In 2011, a disaster shook the entire planet. A massive tsunami, rising nearly 50 feet high, slammed into Japan's coastline. In just minutes, more than 20,000 lives were lost, and hundreds of thousands of homes were erased from the map. The sheer scale of destruction stunned the world and left Japan facing a hard truth: its existing defenses were no longer enough. That unimaginable loss pushed the country toward an extraordinary decision: to build one of the largest tsunami protection systems ever attempted. Along Japan's eastern shoreline, an enormous concrete seawall began to take shape, stretching for nearly 250 miles. But constructing walls almost 50 feet tall, capable of resisting the impact of millions of tons of rushing seawater, was no simple task. It required the coordination of tens of thousands of engineers, cutting-edge machinery, and construction methods measured with near-perfect precision. Yet one critical question still lingers. Can this massive concrete barrier truly defend Japan against the tsunamis of the future? Let's explore the technology behind it. For generations, Japan's northeastern coastline has lived under a constant and invisible threat, one feared across the globe: earthquakes and tsunamis. Japan sits directly above the meeting point of four enormous tectonic plates, a violent collision zone where the Earth's crust is always in motion. This relentless pressure results in more than 500 earthquakes every single year. When these plates suddenly shift beneath the ocean floor, the seabed can rise or collapse in seconds. That rapid movement displaces vast volumes of water, lifting colossal waves that race toward land with unstoppable force. These tsunami waves can tower dozens of feet high, carrying the energy of millions of tons of seawater. In the past, residents of small coastal towns were trained to react instantly. When warning sirens echoed through loudspeakers and the ground began to shake, people knew to run for higher ground without hesitation. But nothing prepared Japan for what happened on March 11, 2011. A catastrophic magnitude 9.0 earthquake tore through more than 300 miles of tectonic plate boundary beneath the Pacific Ocean. The result was a tsunami approaching 50 feet in height, far beyond anything Japan's defenses had ever been designed to withstand. That single wave claimed over 20,000 lives, destroyed more than 120,000 homes, and triggered a nuclear crisis at the Fukushima power plant. The existing seawalls, built to handle waves of only around 26 feet, were completely overtaken. It became painfully clear that the earthquake was just the trigger. The tsunami itself was the real force of destruction. In response, Japan launched an unprecedented engineering effort. Nearly 250 miles of tsunami defense walls were constructed, each standing between 45 and 50 feet tall, with foundations driven as deep as 80 feet into the ground. This concrete barrier was never meant to stop every wave entirely. Instead, its purpose was to slow the tsunami down, buying precious minutes that could mean the difference between life and death. More than $12 billion were invested, not only in the walls themselves, but also in improved warning systems and evacuation infrastructure. The message was clear and resolute. Tsunamis may strike again, but the tragedy of 2011 must never be repeated. The journey began in research laboratories. Engineers gathered extensive data from the 2011 disaster and recreated tsunami conditions inside massive wave tanks. Using scaled-down models, they carefully studied how waves collided with the wall, how water spilled over the top, and how different shapes and materials affected performance. Only after countless experiments did they move forward with the final design. After countless experiments and simulations, engineers continuously refined the wall's design, adjusting its height, thickness, and slope, while also reinforcing the foundations to ensure the structure wouldn't be toppled by waves crashing over the top. Only when scaled models consistently demonstrated maximum resilience did they finalize the plan: the 14 to 15 meter tall seawall with foundations driven 20 to 25 meters deep, a broad trapezoidal base, and a reinforced steel core built to withstand even the most extreme tsunamis. With the design locked in, the next challenge was deciding the precise route for this monumental barrier. The wall would stretch nearly 400 kilometers along the Tōhoku coastline in northeastern Japan, the very region hardest hit by the 2011 disaster. It spans the prefectures of Aomori, Iwate, Miyagi, and Fukushima, forming the longest, most continuous coastal defense system in Japan's history. Once the route was mapped, construction crews began clearing the land. Old homes, damaged infrastructure, power lines, and pipelines were removed. Simultaneously, they built temporary access roads, material yards, crane platforms, concrete mixing stations, and drainage systems to allow uninterrupted work, even during the rainy season. Because much of the Tōhoku shoreline sits on soft, sandy soil, engineers first conducted detailed surveys and reinforced the ground. Deep concrete or steel piles were driven into the soil, layers of crushed stone and compacted sand were added, and the surface was stabilized. The goal was to create a foundation capable of supporting a towering wall without sinking, shifting, or cracking over time. Once the soil was secure, massive foundation pits were excavated in certain sections, some exceeding 20 meters in depth. Close to the shore, temporary retaining walls or cofferdams were erected to keep seawater at bay. Then, a base layer of concrete was poured, followed by dense steel reinforcement cages and massive foundation blocks that formed an incredibly heavy and wide footing, ensuring the wall could resist the relentless force of the ocean. Above these foundations, workers assembled tall, thick rebar cages according to the optimized lab design. Formwork was positioned, and concrete was carefully pumped into each mold section by section. Each block, often several dozen meters long, was poured, cured, inspected, and seamlessly connected to the next, creating one continuous coastal barrier. On the ocean-facing side, specialized concrete units such as tetrapods and other energy-dissipating blocks were installed. These were stacked in multiple layers around the base to absorb and break the waves before they struck the wall directly. Some segments featured stepped faces, sloped surfaces, or splash-reducing ledges to further minimize water surges. On the landward side, soil and crushed rock were added, along with drainage channels to prevent water from pooling behind the wall. Many stretches include inspection walkways or access roads on top, and in certain towns, the seawall even functions as part of the local roadway. Railings, fences, safety ladders, and signage were installed to ensure the public could safely use these areas. It's important to understand that this represents only the general blueprint for the project. Since the seawall spans nearly 400 kilometers, engineers had to make small, localized adjustments in each area to account for variations in terrain, soil conditions, and coastal depth. These modifications were minor and never altered the overall design or structural integrity of the tsunami barrier. In certain sections that demanded extra thickness and resilience, crews reinforced the outer surface with layers of precast concrete blocks. These interlocking panels were carefully lifted into place by cranes and arranged in a precise, uniform pattern. The result was a protective armor layer, designed to minimize erosion and ensure the wall could withstand relentless wave action for decades. In busy port cities such as Iwaki, special engineering solutions were needed to allow ships to continue entering and leaving harbors. One solution is the top-down tsunami gate, a massive steel panel suspended between two concrete towers and operated by hydraulic motors and pulley systems. When a tsunami warning is triggered, the panel drops vertically, forming a solid wall that blocks incoming waves. In other ports, a bottom-up gate is used. Normally, the gate lies flat on the seabed, allowing uninterrupted maritime traffic. When a tsunami approaches, a hydraulic system lifts the gate from below, locking it into the sidewalls to create a strong barrier against the surge. This approach works well in areas without overhead space for towers and ensures ports remain operational 24/7. Because these gates remain submerged, they are constructed with highly corrosion-resistant steel and tightly sealed hinges to endure constant pressure from water and sand. This completes the category of construction techniques used to build Japan's tsunami defenses. Once finished, the nearly 400-kilometer seawall along the Tōhoku coast became Japan's longest and most continuous coastal defense system. The project cost over $12 billion and mobilized more than 30,000 engineers, construction workers, and geotechnical specialists, along with thousands of heavy-duty machines operating non-stop for decades. Hundreds of individual wall sections were built simultaneously, each with customized foundation treatments, concrete structures, and reinforcements tailored to local terrain. Once completed, simulations showed that this advanced seawall system could reduce the force of incoming tsunamis by 30 to 50%, providing several critical extra minutes for evacuation. That additional time could save tens of thousands of lives in a major tsunami. Roads, fishing ports, and residential areas that were once devastated are now far better protected, dramatically reducing the risk of catastrophic damage. While no barrier can completely stop every tsunami, this 400-kilometer seawall represents Japan's ultimate line of defense, giving the nation greater confidence against one of the world's most dangerous natural threats. So, what do you think? Can this colossal seawall truly defend Japan from future tsunamis? Share your thoughts in the comments. We've gathered insights from multiple sources, so if anything seems inaccurate, feel free to point it out. But don't click away just yet. Japan's underwater tunnel engineering is about to amaze you just as much. Constructing tunnels beneath the sea is an extraordinary challenge. These environments are completely isolated, subject to extreme pressure, and the geological conditions can shift every few meters. Completing such tunnels is a remarkable demonstration of Japan's engineering expertise and its steadfast determination to conquer the forces of the ocean. Today, underwater tunnels are an essential part of modern transportation infrastructure, and Japan stands among the world leaders in this technology. Japanese undersea tunnels connect islands, span deep bays, and solve major mobility challenges, particularly in regions where bridges or ferries can no longer meet growing demand. Thanks to these tunnels, travel between coastal areas has become faster, safer, and less dependent on weather conditions, while ensuring a steady flow of goods and passengers to the country's busiest ports. These tunnels have evolved into critical economic lifelines, enhancing Japan's competitiveness and opening new avenues for regional development. However, building such structures requires painstaking preparation, precise geological surveys, careful design, and near-perfect execution to guarantee safety under the immense pressure of the seabed. The first stage begins with a thorough survey of the seabed. Engineers analyze the underwater topography, collect soil and rock samples, and study the structural composition of the seabed to evaluate its load-bearing capacity and identify potential hazards. At the same time, environmental concerns are carefully considered. The project team assesses the tunnel's potential impact on marine ecosystems, working to protect local species and minimize disruption to natural habitats. Measures like noise reduction during construction are implemented, and sometimes artificial reefs are created to provide new habitats for marine life. Once these surveys are complete, actual construction begins. One of the most widely used methods is the immersed tube technique. This process starts on land, where massive reinforced concrete tunnel segments are prefabricated. Each standard segment measures roughly 217 meters in length and weighs over 73,000 tons. These enormous segments are built with incredible precision to ensure perfect alignment and watertight sealing when submerged. Inside each segment, multiple compartments serve different purposes: 2 main chambers for highway lanes, a railway corridor, and a dedicated service passage for future inspection and maintenance. Once each tunnel segment is complete, it is transported to the sea and carefully lowered into pre-dredged positions on the seabed using floating pontoons and specialized cranes. The segments are then connected one by one, forming a continuous tunnel of the required length. The most critical part of this process lies in the joints between segments. If these seals are not perfectly executed, even a small leak could allow seawater to infiltrate the tunnel, creating serious hazards. To prevent this, engineers insert rubber gaskets between each segment to ensure watertight connections. Layers of sand and gravel are also placed around and above the structure to counteract buoyancy caused by the immense water pressure. Only after the joints are securely locked and stabilized are the temporary end bulkheads removed, transforming the separate segments into a single, seamless, watertight tunnel. It's important to note that the immersed tube method works best in areas with stable seabeds and relatively calm water currents. In locations with strong turbulence or complex underwater terrain, this technique becomes impractical due to the challenges of anchoring the segments and maintaining waterproof integrity. Once construction is complete, the next essential step is a thorough safety inspection and operational assessment. Modern tunnels, both submerged and underground, often feature 2 levels, effectively doubling traffic capacity without expanding the tunnel's footprint. Vehicles can travel at consistent speeds of around 60 km per hour, while emergency exits are spaced every 200 meters. Engineers perform a wide range of rigorous tests before opening, including waterproofing checks, pressure and structural resistance evaluations, fire safety assessments, and ventilation system performance tests. But a tunnel's journey doesn't end when it opens. Long-term maintenance is crucial to ensure safety and longevity. Technical teams conduct regular inspections of the concrete lining, waterproof membranes, support structures, and drainage systems to detect any signs of deformation, cracking, or wear. Hundreds of sensors continuously monitor pressure, temperature, humidity, and vibrations, sending real-time data to a central control center where engineers can detect even the earliest indicators of structural fatigue. Specialized vehicles perform routine cleaning and sediment removal using high-pressure water jets and suction systems to keep the tunnel floor clear and prevent blockages. Thanks to this combination of advanced sensor technology and meticulous hands-on maintenance, Japan's underwater tunnels can operate safely and efficiently for decades. They withstand the extreme pressures of the ocean depths while standing as a testament to human ingenuity and engineering resilience. Through these extraordinary projects, from towering tsunami seawalls to deep undersea tunnels, Japan showcases not only its cutting-edge engineering but also the resilience and determination of a nation that always rises stronger after disaster.